Section 9.4 is real numbers. I can compare and order real numbers. In lesson 5.1, we learned that a rational number is a number that can be written as a quotient of two integers. All rational numbers have decimals that either terminate or repeat. An irrational number is a number that cannot be written as a quotient of two integers. The decimal form of an irrational number neither terminates nor repeats. Okay, numbers like pi and the square root of 2, for example, never terminate, never repeat. We can't write them as a fraction, so they are irrational, not rational. The real numbers consist of all rational and irrational numbers. So any number that you've ever worked with is a real number, any number you know. In example 1, we're going to classify real numbers here. So 5/8 in decimal form, remember we take 5 divided by 8, and here I get 0.625. My decimal type here is terminating. Because it ends after the 5, it's terminating, as in it stops. So because it's a terminating decimal here, I have a rational number. And we can tell from our number itself because we can write it as a fraction. 5/6, again we take 5 divided by 6. 6.8333, okay, that 3 is repeating. So our decimal type here is repeating. And because we have a repeating decimal, it's a rational number. Okay, think about it as terms of like a rate. Miles per hour, for example, is a rate, and it's a fraction. Miles per hour. Because we can write it as a fraction, we know it's rational. And because our decimal is repeating, we know that it's rational. The square root of 19, however, in decimal form, 4.358889844. Our decimal type here is neither. It doesn't terminate, it doesn't repeat. And if you're looking at your calculator right now after taking the square root of 19, you're going to say, well, it stops after this 4. It doesn't. That's just all that our calculator can show. Okay, so it goes on further. It's just my calculator, for example, only shows this many digits. So it doesn't terminate and it doesn't repeat. So here, since it doesn't do either of those things, it's irrational, as in not rational. We can't write that as a fraction. Rule of thumb. So besides pi, most of your irrational numbers are going to be square roots. So if you see a square root, we have to double check, is it a perfect square? If it's a perfect square, something like the square root of 16, for example, which as a decimal is just 4, okay, that terminates, which makes it rational. But any square root of a number that isn't a perfect square, so 19 is not a perfect square, 51 isn't a perfect square, 97 isn't a perfect square, okay, those would all be irrational. The square root of 4, the square root of 9, the square root of 16, square roots of perfect squares give us exact values, exactly 4, exactly 2, exactly 3, exactly 4. So those are rational numbers. Now, feel free to pause here and give this a try if you'd like. We're going to determine whether each number is rational or irrational. 2/3 is written as a fraction. That means it's going to be rational. If we wanted to write it as a decimal, we could. It'd be 0.6 repeating, which again, because it's a repeating decimal, tells us it's rational. The square root of 100 is 10. 10 is a terminating decimal. So this here is rational. The square root of 6, however, is the square root of a number that's not a perfect square. 6, not a perfect square. When I take the square root here, I get 2.449489743. Okay, since it's not the square root of a perfect square, my decimal doesn't terminate, it doesn't repeat. Here, it's irrational. And then number 4 here, remember we can split this up as 2 square roots. I can take the square root of 16 and the square root of 25. The square root of 16 is 4. 4 times 4 is how I get to 16. The square root of 25 is 5. 5 times 5 is how I get to 25. And since both of those are integers, I can divide them and get 0.8 if I'd like, which is a terminating decimal. Here it's rational. So again, we have to be careful when we see square roots. If they're square roots of perfect squares, they're still rational. If they're square roots of numbers that are not perfect squares, they're going to be irrational. In example 3, we're going to order the numbers from least to greatest. So here it's going to be helpful if we can get these into a form that's more comparable. So 4/3 is 1 1/3. Or if I take 4 divided by 3, I get 1.3 repeating. Negative 2.8 is already a decimal. The square root of 3 we know is in between 1 and 4. 3 is in between 1 and 4, so its square root is in between 1 and 2. And it's going to be closer to 2 because 3 is closer to 4. So this is about 2, a little less than. And if we do it as a decimal, the square root of 3 is 1.73-ish. Square root of 5, 5 is in between 4 and 9. 5 is a little bit closer, and this is going to be on the negative, like the smaller side. So it's going to be 1 point something, close to 2. 5 is in between 4 and 9, closer to 4. So its square root is going to be closer to 2, but it's going to be more than 2, so 2 point something, and negative. So if we check this, it's going to be negative square root of 5, negative 2.24. So again, the square root of 3 is in between 1 and 2, closer to 2. And the square root of negative 5 is in between negative 2 and negative 3, closer to negative 2. So to put these in order from least to greatest, we can use a number line if we want to. Four thirds is 1 1/3. I forgot 0 here. 1 1/3, about here. Negative 2.8 is past negative 2, close to negative 3. 1.73 is closer to 2. And negative 2.24 is closer to negative 2. So, first we have negative 2.8, which again, if we used our decimals, we could see that as well. Then we have negative square root of 5. Then we have 4/3 is our third dot. And my last dot is the square root of 3, about 1.73. So there we have our numbers in order from least to greatest. Feel free to pause here and give this a try for number 10. Again, 2.9 is just 2.9. So on a number line, it's going to be almost 3. The square root of 10, 10 is in between 9 and 16 as far as perfect squares go, closer to 9. So when we take the square roots, it's going to be close to 3, but it's a little bit past 3 because it's in between 3 and 4. Here, square root of 10. If we type that in our calculator to get an approximate value, we get 3.16. 7/3, 7 divided by 3 is 2, with 1 as our remainder, so 2 1/3. So a little bit past 2. And 2 square roots of 2 is 2.82. Right here. So from least to greatest, we have 7/3, then 2 square roots of 2, then 2.9, and then the square root of 10. And again, we can compare our decimals as well. If we don't want to use a number line, we don't have to. 2 1/3 is 2.3 repeating. So here, my smallest value, and then 2.8 is smaller than 2.9, and all of those with 2 as our ones digit are smaller than 3 as our ones digit. So we can put them in order that way as well. 11 here. 16 divided by 3 is 5 with a remainder of 1, so 1/3. This is -5 and 1/3. So it's going to be a little bit past -5. Third of the way past. Negative square root of 22. 22 is in between two perfect squares, 16 and 25. It's closer to 25, which means it's going to be close to 4, or close to 5, sorry, closer to 5 than to 4. Keep in mind these are negative, so it's going to be closer to -5 than it is to -4. And if we take the decimal approximation there, it's about 4.7. And negative. -3 square roots of 2. Square root of 2 is a little under 1.5. It's 1.4. Times 3 is going to give you -4.2. If you're not sure, take -3 times the square root of 2, and we get -4.24. 4.24 here. -3 square roots of 2. And -4.6 goes in here too. So all of these are pretty close, so using a number line makes it hard. But if we can compare our decimals, I have -5, -4.7, and -4.24. The smallest number is -5 1/3, which is actually -16/3. Then our next smallest decimal is -4.7, which is actually -square root of 22. Then -4.6, which is just -4.6. And last, -4.24, which is -3 square roots of 2. So again, if we switch these all to decimal form, we can compare them and put them in order. And that's all I have for section 9.4.